Okay, so now we're going to wrap up the chapter on fluid statics, and that's with a discussion on buoyancy and stability. So for buoyancy, let's consider an object that is not partially immersed in the fluid, that doesn't just have one side of it that is in the fluid, but let's consider an object that is completely immersed in the fluid. So for this, the picture looks something like this, where we have some sort of submerged object, and it's completely submerged. There's water on all sides of the surface. And we want to find the so-called buoyancy force, and the buoyancy force is nothing more than the net force produced on the object by the fluid. Okay, and so then the net pressure force. So then if you want to find the net force of the fluid on this object, we would really have to just integrate the net pressure forces, right? Because we have some sort of solid object, and we want to find the net forces. Well, we have two choices. Those are the viscous forces from shear stress, or the pressure forces. And of course, we don't have viscous stress because we're assuming the fluid is static and not moving. So to find the net forces, we just need to integrate the net pressure on the surface of the object. Okay, and so, and that's one way to find the buoyancy force. And in fact, last year in your homework samples, there's a problem it's actually a buoyancy problem, but it was given before buoyancy was discussed. And the problem asks you to find the pressure on the top of a cube and the pressure on the bottom of a cube. We'll call that P bottom. And then you know the gamma of the cube, and then you're asked to find the tension. And this is really a buoyancy problem because it's completely submerged in the fluid, but we are actually integrating, it's a simple shape, and we're actually integrating the pressure forces on the surface of this cube. Okay, and that's basically what we are doing. And at the time when I assigned this, we did not go over buoyancy yet, but we did go over the pressure distribution. And so we can do, and so basically we just need to find the integral of minus p n hat dA to find the net buoyancy force. But we can be a little bit clever here. And so let's just consider a fluid element, because really what we want are the pressure forces, right? And that's it. And those are a bit of a pain because this integral is not easy to do, especially if the shape is really complicated. But can we relate it to something far simpler? Well, why don't we know that the fluid is in static equilibrium, so why don't we take this solid object and replace it with the fluid element that has the exact same shape? Okay, and so I'll just shade this blue. So this here is a fluid element that has the exact same shape. And we are interested on finding the pressure forces on the edge of this fluid element, because those will be the same pressure forces that are pushing on the edge of the actual solid. Okay, and because it's in static equilibrium, we can apply the static equilibrium condition to this fluid element. Okay, and there is one more force. We got the pressure forces basically pushing on the surface. And we have weight, which is mg, okay? And so those are the only forces we have. So we're going to apply static equilibrium. So for the fluid element, for static equilibrium, we know that the sum of forces is equal to 0. And that's equal to the weight plus the integral of the pressure forces, right? It's not moving, and there's only weight, and there's only pressure force. That's it. And we know that the weight is just the integral of density times gravity. And we know that the integral of the pressure forces, which is what we are after, is just minus the integral over the area of minus p n hat dA. And that's equal to 0. So this implies that the pressure forces is equal to the opposite of the pressure forces, there should be a minus sign, or yeah, there's because it's minus, that the pressure forces are just equal to the weight of the fluid. Okay, so this here is just the weight of the fluid in the element, and these here are the net pressure forces on the surface. Or if rho and g are constant, you can pull those out, and it just becomes rho g times the integral over the volume of dv, which equals rho g v. Okay, so if rho and g are both constant, and a lot of times they are, and a lot of times rho is not constant, you just need to be careful with that, you have that the integral of the pressure forces on the surface is just equal to rho g of the fluid. That's it. Okay, then the buoyancy forces is equal to minus p n hat dA, and that equals minus rho g minus the density of the fluid times gravity times the volume. Okay, or that the buoyancy force, if rho and g are both constant, is just equal to rho g, is just equal to the weight of the fluid. Okay, and notice that the direction is in the opposite of the buoyancy force, is in the opposite direction of g. So the buoyancy force so the buoyancy forces tend to cause objects to float, and that is basically because if we have a submerged object, and I'll just draw it as a cube, the pressure is higher on the bottom of the cube than it is on the top. So the fluid pressure forces are pushing up on it. Okay, so there's a net upwards force if gravity is pointing down. Okay, and this is so-called Archimedes' principle, and and the line of action passes through the center of mass of the displaced fluid, not the object. It passes through the center of mass of the displaced fluid, is where the line of action is. Okay, so the net buoyancy force would then point up, and its line of action is through the center of mass of the displaced fluid. So that's if it's complete. If an object is completely submerged. Now, what about if an object is partially submerged? Okay, what do we do then? And a common example for that would be a boat. Well, here the same for such a case, you cannot use that formula. You would actually have to go through and actually do a formal volume integral. Okay, but in some cases, like a boat, you can actually simplify it a bit, and by basically noting that usually it's some sort of water surface and air above it. And so you would have displaced air above it and displaced water below it. And so you can do the formal, you can do the very formal integral, because as you go around the object, and if you did a fluid element, well, this top half of the fluid element would have air in it, and this bottom half would have water in it. So the density would not be constant, and it would be a function of position, and you need to take that into account. So the net buoyancy force, and you need to use the integral. And so the net buoyancy force would be the integral minus p n hat dA, which again is horrible to do, but we can do a volume integral of rho g dV, and that's about as far as you can take it. And so with that picture, it would look so yeah, then the buoyancy force, because g is normally constant, would just be minus the integral of rho dV, and this is really still the displaced weight of the fluid. It is nothing more than that. It's just that it's a bit more complicated because the density of the fluid that is being displaced is different on different portions of the object. Okay. and the force passes through the center of mass of the displaced fluid. Now, in the case of something like a boat, where you have air over here and water down here, well, essentially the buoyancy force due to the air is going to be essentially zero, or 1,000 times less than it is in the water. So for something like a boat, when you want to consider the buoyancy forces, you really only need to consider the submerged portion. Okay, and that's it. But if you have something more complicated, like say in the deep sea, they have these things called brine pools, where on the bottom of the ocean you have brine, which has a density that is greater than that of H2O, and then above the brine pool you have seawater. Okay, and a brine pool just is a region where the salt content is about 3 to 8 times higher than the seawater, and the density of seawater increases with the increasing salt content, and so you wind up with these brine pools, and they look like little undersea lakes, which they're fascinating, and actually submarines can actually float in these brine pools because the water here is more dense than it is over here. And in such a case, if there was something floating in this, in such a case, you would need to do the formal integral and consider the buoyancy force from the top half and the buoyancy force from the bottom half. Okay, because the density here is not 1,000 times less than the density here. Okay. So you just need to be careful in the general case. You need to do the formal integral and just keep track of basically the density as a function of position. Okay, but in any case, the buoyancy forces passes through the center of mass of the displaced fluid. So we'll do a little example problem. So here we have a lake or a river or something like that. We have a heavy rock, we have a tether or a rope, and we have a timber attached to it. The total length of the timber is 2 meters. The cross-sectional shape is here. It's 0.35 meters by 0.15 meters. And the first 8 meters of the timber is submerged. Okay? And so we are asked to find what is the specific weight of the wood and what is the tension in this rope. Okay, we know that gravity is pointing straight down and we have atmospheric pressure here. Well, the fluid properties, we just sort of write them down, and we know that gamma of H2O is 9.8 kilonewtons per cubic meter, and we know that the density of water is 1,000 kilograms per cubic meter. So we then so now we want to analyze that. We want to find this, and to me, it's not obvious how to find the specific weight of the wood. It would seem to me that we would normally need to know that. And so when you are left with a problem where you don't really know where to begin, what you do is you start applying the fundamental concepts that you do know about it. We know that this is a stationary lake, so we know that basically this timber should be in static equilibrium, right? So our foundational principle that we need to apply is static equilibrium, and meaning that there should be no net moments and there should be no net forces in the system. So let's just perform that analysis and see what happens. Okay, and you sometimes said the same thing in thermodynamics, where it wasn't really obvious how to go about solving a problem, so you just applied conservation of mass and conservation of energy, and perhaps the second law of thermodynamics, to basically apply those to your problem and see what those would tell you. Okay, and sometimes you came up with, and sometimes those turned up nothing, but sometimes those basically helped out. Okay, so let's do a free body diagram, because we know that this is in static equilibrium. I mean, this is the fluid statics chapter after all. So we have a free body diagram here. We have our timber. We have a buoyancy force here, and we have the weight of the timber here, which we don't know. Okay, but we do know that the total length of the timber is 10 meters. It has a constant cross-sectional shape, so wherever the weight is of the timber, it's going to point straight down, and it's going to act halfway through at the midpoint of the timber, or 5 feet, or 5 meters, I should say. Okay, and then the buoyancy force is going to act straight up. Again, it acts opposite to gravity. We need to find that. And its line of action is in the center of mass of the displaced fluid. Well, only the first 8 feet, or first 8 meters of the timber is submerged. And the center of mass of a rectangle of a prism with a constant cross-sectional shape is exactly half of that. So it is only 4 meters. And technically, if I was to zoom in, there would be, and the timber would look something like this. You have the timber here, and you'd have a goofy little triangle here that we are neglecting because the timber is making an angle, and the surface of the water is horizontal. We are assuming that basically this small piece is extremely small compared to the total length of compared to the rest of the volume. So we are neglecting that. Okay, but there is a little bit of an error, basically due to that, by basically treating it to be so simple. Okay, so now let's go through and find all the geometrical information that we know. So we know where the buoyancy force is going to act, and we know where the weight is going to act, and we also have a tension force that is pulling the timber down. Okay, and we're going to assume it's going to be at some angle theta, which we also don't know. Okay, so let's just apply a static equilibrium analysis after we find the volume of the wood, and that's just the length times the cross-sectional area, and you get a 0.525 cubic meters. The volume of the submerged object, or of the submerged portion of the wood, which is this portion right here, is just 8 meters times the cross-sectional area, and you get 0.421 cubic meters. So now the wood is in static equilibrium, so we can just perform, and there are no forces in the x direction, so that wouldn't tell us anything. So let's just sum the forces in the y direction. So the sum of f of y is equal to 0. We got the buoyancy force going up, we got the tension force pulling it down, and we got the weight trying to pull it down. And the sum of those has to be equal to 0. And we got the sum of the moments are also equal to 0 because it is not rotating. Nope. So we need to sum the moments about a point, and let's just sum them about the connection point of the rope, and I'll call that point A. Okay. So we have the sum of the moments about point A, and I'm going to use counterclockwise as positive here. So we have the buoyancy force times the moment arm, and turns out that would be just 4 meters times a cosine of this angle here, and we have a moment produced by the weight, and that would be just the weight, which we don't know, times the moment arm, which is this distance here, which would be 5 meters times cosine theta, and that's equal to 0. Okay. Well, notice that both these terms have the same cosine theta, so the cosine theta drops out, and it turns out we do not need to know what theta is. Okay, so we can then solve for the weight in terms of the buoyancy force. Okay, so solve for the weight, and we get that basically weight is just 4/5 of the buoyancy force. And weight is equal to the specific weight of the wood times the volume of the wood. Okay? And we know that the buoyancy force is just equal to the specific weight of the water times the volume of the submerged section, right? Because basically the buoyancy force is just due to the portion of the wood that is submerged. Okay, so this implies we basically substitute these in here into our moment equation, and what we get is that this implies that 4/5 gamma of H2O times the volume of the submerged section is equal to gamma of the wood times the volume of the wood. Well, we can solve for gamma of the wood, which is something that we're trying to find. So gamma of the wood is equal to gamma of the water times 4/5 times the ratio of the submerged volume to the volume of the wood. Okay, so we now know all of these things. We stick them in. We know now that gamma of the wood, or the gamma of the water, is 9.8 kilonewtons per cubic meter times 4/5 times 8 meters times the cross-sectional area divided by 10 meters, which is the total length, divided by the cross-sectional area. These all cancel out. And we are left with that gamma of the wood is equal to 6.272 kilonewtons per cubic meter. So it is quite a bit lighter than the water, and that's not surprising. It should be because the timber is trying to float, but it's being held back by a tether. Okay, so now we know the specific weight of the wood. Now we can apply the sum of the forces in the y is equal to 0. So from that, we get that the tension is equal to the buoyancy force minus the weight. And the buoyancy force is just gamma of the wood times the volume of the submerged section, or gamma of the water times the volume of the submerged section, and the weight of the timber is just gamma of the wood times the volume of the wood. And we now know all of these pieces, so we can now stick in the numbers, and this turns into 9.8 kilonewtons per cubic meter times 0.421 cubic meters minus 6.272 kilonewtons per cubic meter times 0.525 cubic meters. And you stick it in, and you wind up that the tension force is 0.833 kilonewtons acting down. Okay? And so this is actually one of those problems that it actually turns out to be very nice. If you just apply the principles and start working through them. Because to me it was not obvious of basically where to start. We're basically to start this problem. So we just apply our basic principles and see what they tell us. At worst, they're going to tell us nothing useful. Okay, and so that's it for buoyancy. It's a fairly straightforward concept. You just need to find the volume of the submerged and multiply that by the weight of the water, and then that's the buoyancy force in most cases. Again, if you're doing like a brine pool or something like that, there are some special cases that you need to worry about. But those are few and far between. So now for stability, now we got to consider if you have a boat and it's floating, is it going to be stable? And what I mean by stable is if you slightly give this a surface a twist, is it going to capsize and tip over? Is it going to tip over and sink? Which, if you're designing a boat, you really, really, really don't want to happen. And that's going to depend on where the center of mass of the object is. Okay? And we're not going to go through this in detail, just the real basic concept. Okay? And so, let's just consider a picture here. We have a floating object here, and the center of mass is I'm basically drawing it below. So we have some mass times gravity of the object below and some net buoyancy force going up. Okay, and so here we have a case where the center of mass is below the displaced, is below the center of mass of the object is below the center of mass of the displaced fluid. So that implies that if we tip it to the side, what's going to happen is that the buoyancy force is going to act up, and the weight's still going to try to pull it down, but there's going to be a net moment produced by these two that is acting counterclockwise, and that counterclockwise motion is going to tend to basically basically turn the vessel over to the right direction and then not sink. Okay, so this is called a stable configuration. Here, weight and the buoyancy force make a moment which restores the vessel upright. Now, if we have the opposite thing, like say we had a big mass, huge mass sticking on top that had a weight on top of it, and that would look something like this. So here, if we have the center of mass of the object above the center of mass of the displaced fluid, the buoyancy force still acts up, and the weight of the object still acts down. But notice here, we have tipped it this way, and the moment is actually acting in the direction that we tipped it, not in the opposite direction, like in this case here. So essentially then, this case is unstable because the buoyancy force is going to tend to cause the object to continue to tip over, and eventually it will capsize. So this is called an unstable configuration. And here, mg, our weight and the buoyancy force conspire to make a clockwise moment, which will make the vessel tend to overturn. Okay, where here in the stable configuration, the moment produced by buoyancy forces is basically fighting any motion that tries to overturn it. Okay, and so this here is just a real basic overview of the concept of stability. If any of you ever design ships, you're going to be dealing with this quite a bit. And that is it for fluid statics.